So let me emphasize again, number 19 is tougher than I would ask on a test, probably even tougher than I would ask on a quiz. Maybe it would be fair game as a bonus question. That I'd be okay with. But if you're asking, am I going to throw one like this on the written section of a test? No. Number 19 says this: a car is traveling at 20 meters per second when the driver sees a child standing in the road. He takes 0.8 seconds to react, then steps on the brakes and slows down at 7 meters per second squared. One of the first things I noticed here is I saw slows down. So Manraj, I said -7. Okay. How far does the car go before it stops? I had to divide this up into sections. So I said, okay, here's the car. Here's the person. I said, this is the total distance they want us to find. I think this is going to be two parts. I think there's going to be before they hit the brakes while they're coasting, and then after they hit the brakes while they're slowing down. Kind of the same way we divided the playground slide into parts. Now, how did I know that this has to be in two parts? I'll convince you of that partway through. So I did this. And then I started to go through the question, looking for physics words and numbers and saying, okay, what side do they go on? And by the way, I think what I'm going to do is I'm going to figure out how far the car travels while coasting before hitting the brakes, how far the car travels while braking, and I think the total distance, I'll add them up. There's the argument. And the moose question is very, very similar. Okay, what's that 20? Well, it's meters per second, so it's a velocity. VI or VF? I think it's VI while coasting. You okay with that? 0.8 seconds to react. I think that's a time we're still coasting because we haven't hit the brakes yet. It took the driver that long to react. -7 meters per second squared. I said, you know what? That's got to be while braking. And as I was doing this, I was checking the units and I noticed they were all good. Before stopping, I know VF is 0. Problem, I only know 2 things. I need 3 things to find the fourth. I only know 2 things. I know 3 things to find the fourth. And here's where I'm going to get a little bit clever. In this section right here, have we hit the brakes yet? So we're not speeding up or slowing down. We're not accelerating. If we're not accelerating, what is A exactly as a number? That's a velocity. What would A be? What? Yeah. I said, I think I can safely assume that now I know 3 things, I can find the fourth. Which equation would I use here? Well, I have a D, a VI, a T, and an A in it. I would use D equals VIT. Technically plus a half AT squared. Why didn't I bother writing the plus a half AT squared?
Because it's all 0.
What's 0?
A.
A is 0, and so half AT squared is going to be 0. Okay, I'll come back to you in a second. So, while we're coasting, have we sped up? Have we slowed down?
No.
So can't I also say, right when I start hitting the brakes, you were looking down. Got to look up. Stay with me. Right when I hit the brakes, I think I can safely say that VI is still 20. Because it was 20 right here. I think it's 20 for that whole section. And now I can find D while braking. It's going to be, I think, VF squared equals VI squared plus 2AD. Get the D by itself. And the total answer, add them together. Now I'm going to pause. Technically, did I do anything new there? I was clever. And I've seen enough of these that I can fit things in better. Now, how did I figure out there had to be 2 parts? Because We're accelerating to slow down, but there was the reaction time where we weren't accelerating. There has to be two parts, in my mind. Ron, you had a question? Yeah.
You said, you think A is 0. When you're final velocity, E20, is it going
So you could also do it with that, yeah. And yeah, then you would use, and we're at the stage now where you will often find you have more than one approach that will work. So you could also use, good call, D equals VI plus VF times T over 2, and you'll get the same answer. By the way, what's VF? What did you say it was? 20 plus 20 divided by 2, you get 20. You'll get the same answer for either of those. Yep, totally. Yes?
If there was a question where you had multiple different ways to get your answer,
I take both.
if you did though, would you get extra marks?
No, but on a test, you can check your answer by finding it two different ways. Right? Lesson 5, acceleration and G's. Galileo showed that near the Earth, if we ignore air resistance, so if we go in a vacuum, all objects fall to the Earth at the same acceleration, regardless of their mass. What? A feather in a vacuum will accelerate at exactly the same rate as a bowling ball. Put your pencils down, look up.
Vacuum. How do you think it back something fall in the vacuum?
Let's find out.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems, and that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of, so they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest.
Are we in a vacuum yet?
No.
So which one will fall, which one will accelerate faster? That's what you're all used to. But from now on, we're going to do our free fall physics assuming things are in a vacuum, unless I say different. Once in a while, we'll look at air resistance, but most of the time, we're going to ignore air resistance.
Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber. We dropped 2 millitorr in the last 30 minutes. But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCB 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
Now we're watching it in slow motion. Don't think that with no air things fall slower, but you'll certainly notice the bowling ball and the feather are falling at exactly the same rate. Are they speeding up? Yes.
Look at that.
They came down exactly the same. Wow.
Look. Exactly. Exactly the same.
Feathers don't move, nothing. Look at that.
That's just brilliant.
Yep.
What would happen if you had a vacuum receiver big enough that you tried to like lift off an airplane?
Yeah, the plane wouldn't fly. Planes need air. They fly due to air resistance. Good question. So objects near the Earth, especially if we ignore air resistance, they'll all accelerate at the same rate. We are going to pretend that whenever we're dropping things, let's assume it's like a bowling ball shape and not a feather. And that way we can ignore air resistance. We use the lowercase letter g to represent the strength of the Earth's gravitational field. When you drop an object, Jaden, it accelerates at negative 9.8 meters per second squared. Did I put that on your green sheet? Can you find it on your green sheet? That's really my way of saying that. Okay. You'll probably end up memorizing that number, but it's on your green sheet if you blank out. And we will be doing a lab activity later on where you'll try and actually measure how fast objects accelerate in free fall. Yeah. No, negative is arbitrary. We're going to, in this unit, let down be negative and up be positive. Okay? In fact, people often talk about g forces. They should really be talking about g acceleration. And so for the remainder of this year, you'll just hear me talk about g's. You'll never hear me say g force. I'll just say, how many g's? And what I really mean is, how many gravitational accelerations? 1 g is exactly 9.8. The negative just says downwards. Found it? Braden, 1 g is exactly 9.8. I'll leave the negative off for now. Or what's a nice round number really close to 9.8 that you can do math with in your head? Yeah, it's about 10. And units, meters per second squared, meters per second squared. 2 g's is exactly 19.6, or around 20. 6 g's is exactly, what is 9.8 times 6?
550.8.
Is that right?
Yeah.
Or about 60 meters per second. Outside of a vacuum, air resistance can dramatically lower g. Next class, you'll see a video of me jumping out of an airplane. And the fact that I'm alive is because air resistance lowered g to near zero. But we're going to ignore air resistance most of the time. To really study air resistance, Liz, you need calculus. We'll look at it every so often as a little snapshot, brief moment in time. But to calculate it, it's a complicated equation formula with drag coefficients and cross-sectional areas. You really need calculus. Human beings can survive up to about 25 Gs in most situations without dying. Although anything over about 10 Gs will often break ribs, etc. All of you right now, lift your feet up off the ground, please. Can you feel the chair pushing up on you? Yeah. That's 1 G. You're all used to it. So if you're experiencing 2 Gs, that's like having one of you sitting on your lap. If you're pulling 4 Gs, that's like having 3 of you sitting on your lap. If you're pulling 10 Gs, that's like having 9 of you dogpiling on top of you or sitting on your lap. 25 Gs, it's always one less because you grow up, you're used to 1 G at all times. That's what you feel pulling you down. In fact, you don't even notice it. Until I told you to lift your feet, you didn't even feel the chair pushing up on you, but it's always there.
So 25 running setup, probably die.
It all depends on what angle your body takes those G's at. We're going to talk about that in a second. Yes?
Is that why, like, if like a grown person were to like, this is kind of messed up, but like punch a child, they would take more severe damage because they have less weight, and the G-force would be greater?
No. The force wouldn't be greater. The force would be identical because Newton's third law says that forces come in pairs. The acceleration would be different, not the force, because and we'll talk about car collisions. In other words, if a semi-truck has a head-on collision with a small car, which is a much better example than a grown-up punching a child, I'm just saying, between the two of them, each will experience the same force. They won't experience the same acceleration, which means they won't pull the same G's. At Playland, the ride with the highest G's is around 4.5. Which ride? If you signed up for Physics 12, I'm hopeful that next year in May, things will be open up enough that Playland will open up. We do an amusement park physics day at Playland where you go on rides with accelerometers and instruments and you measure some of this. They had to cancel it this year and they canceled it last year, but I'm hoping that we'll be back to it next year. Put your pencils down, look up.
Well, in my left hand, I have a feather.
So this is from Apollo 15 on the moon. In his left hand, he's holding a feather.
In my right hand, a hammer. I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here and hopefully they'll hit the ground at the same time. How about that? This proves that Mr. Galileo was correct in here and hopefully, so we thought we'd try it here
Watch
for
it again. Is gravity on the moon stronger or weaker than the Earth?
Weaker.
So if you watch, notice also though, they're falling at exactly the same time, but they're accelerating not at 9.8. On the moon, they're accelerating at about 1.6 meters per second squared. So 1 G on the moon would be about 1.6.
The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here and hopefully they'll hit the ground at the same time. How about that? This proves that Mr. Galileo was correct in his findings.
Wow.
Okay.
Mr. Dick, you really believe that it was not material?
Yes.
I
I just showed you a video from the moon. So there you go.
feel like it's
Turn the page. How do we know that 25 G's is usually fatal? How do we know that 10 G's is what breaks bones? Well, one of the main pioneers is one of my nerd heroes, Air Force doctor named Colonel John Stapp. In the late 1940s and early 1950s, he was commissioned by the U.S. Air Force to design ejection seats for pilots. We had just invented jets. Jets were going faster and faster. We weren't even sure if pilots would survive ejecting. And so a basic question was, should we even put ejection seats in airplanes? Because if they're going to die when they eject, then maybe our best bet is to try and force them to try and land the plane, even if there's only a 1 in a million chance of landing the plane. That's better than a 0 in a million chance if they die by ejecting. And so Colonel Stapp was put in charge of the project, but even though he was a colonel, he felt uncomfortable ordering people to do these experiments, so he volunteered for most of them himself. Read along with me. It says this: Air Force Dr. John Stapp was involved in designing and testing ejection seats for jet fighter pilots. He rode a rocket sled that ran on a special track and was subjected to 15 Gs for 0.6 seconds and a peak of 22 Gs during this photo. So this photo here, he's pulling about 22. And that's why it all depends on what angle it's hitting your body at. One of the things that he showed is we're better at taking Gs from certain angles. He set the world record. His rocket sled was traveling at 0.9 times the speed of sound, Mach 0.9, around 300 meters per second. He came to a stop in 0.68 seconds. How many G's did he experience? We're going to figure it out. First thing we're going to figure out is the acceleration. So everybody write down A equals question mark. What's that 300? V what? How do you know what's VF?
It's after you stop.
So what's VF? Oh, okay. So VI is 300. VF is 0. What's that 0.68? How do you know? And do you notice I'm giving you less descriptive words in my questions? Now I'm expecting you to look at the units and figure it out. T equals 0.68. I'm looking for an equation that has an A, a VI, a VF, and a T in it. There is one. Get the A by itself, please.
Okay.
I'll give you a hint. A equals.
That's pretty simple. This is a 0.
Leave the 0 for now. Just rewrite the equation. A equals, get the VF equals VI plus, so it's the first equation, VF equals VI plus AT. Matt, get the A by itself. What's going to drop down like a domino?
Yeah.
Okay, keep going. Yep.
And then what is VI doing to AT?
What is it doing?
Okay, never mind. That's what we're trying to isolate.
No, we're trying to get A by itself.
Oh, that's right. Sorry. It's adding, so we subtract it.
So minus VI.
Yeah.
Keep going.
And then we have time. What is it doing to A? It's multiplying, so we divide time.
So there's our new equation. You've probably seen that one enough that when you see it, you recognize it and go, oh, yeah, I think I've done it right. So if we plug this in, we're going to get 0 minus 300. By the way, was Colonel Stapp speeding up or slowing down? Am I expecting a positive acceleration or a negative acceleration? So everybody on your calculator, can you try this, please? So get your calculators out if you haven't already. Top's got to be in brackets. 0 minus 300, close bracket, divided by 0.68. What do you get?
441.
Now so I'm going to write negative 441 meters per second squared. Now that's the acceleration. That's not what this question wanted me to find. This question wanted me to find how many. So here's how you find G's. To find G's, it's the acceleration divided by 9.8. Not negative, Braden. The negative is a directional thing, just to find the magnitude. So on your calculator, hit your answer button. Divided by 9.8. How many G's did he pull? And the units for G's is G's. Nope. We're going to watch a video of it. Well, patience, we'll find out. He also, because pilots would be ejecting at high winds, he also exposed his face to 940 kilometer per hour winds in another test. Because again, okay, if the pilot ejects, but sorry to be really gross, his eyeballs are ripped out at that speed, well, that's not what we want either. We need to test all of this. So, put your pencils down, look up. We're going to be watching some videos. It's pretty intense. If you feel a little queasy or nauseous, just look away or close your eyes. Don't feel bad, okay?
In 1947, in the deserts of New Mexico, an Air Force colonel named John Stapp began a bizarre, top-secret aeromedical project.
So this was their first setup before they came up with a rocket sled. You just saw that collision in slow motion. You're going to see it again in real time, and it just looks painful.
That would lead to the development of the first crash test dummies.
Colonel John Paul Stapp is sort of the father of this business in the sense that he was interested in how to protect air crewmen when they ejected out of an aircraft at high speed. He didn't know any
So here's the one at speed.
way to study that other than to subject human volunteers to loading that's very similar.
So that's John Stapp. He felt he should be the one to volunteer. That's him in the chair. He's wearing pressure-sensitive discs that will burst at certain accelerations, at certain Gs.
One of the rules of human volunteer testing is you got to be willing to do it yourself. So he was his own volunteer.
Stapp used this high-speed test track for a terrifying series of experiments.
He started the countdown.
5, 4.
Then, just as he reaches 0, you hit this enormous ram against your back and feel totally helpless. You're being given the biggest kick that could be delivered.
Remember, there was the old saying in the Army, don't volunteer. And in fact, there were several figures in the early days of this kind of work, before there were dummies, who were doing peculiar things. Several of these people became disabled.
Undeterred by the risks, Colonel Stapp pushed human testing to the limit. He was trying to work out the maximum speed at which pilots could safely eject. During a 7-year period,
What's the name of the rocket sled?
Sonic Wind.
Pretty good name for a rocket sled.
he volunteered for 26 potentially lethal experiments.
He did this 26 times. That's a lot. Especially when you see what he goes through to keep volunteering. I'm impressed. This is where we get most of our data for crash test dummies as well, was these experiments here.
So Dr. Stapp kept going faster and faster, and finally in December 1954, he hit his fastest speed. According to the newspaper, 632 miles an hour. According to the calculations I made from feet per second, at one point he hit 639. But the average would be about 632. And he stopped very, very short. Just a matter of a second or less.
Stapp's record-breaking run made him the fastest man on Earth. He endured a massive 43 Gs during the deceleration, the equivalent of smashing into a wall at 70 miles per hour.
As he said, his eyeballs just about popped out.
So all the blood vessels have burst in his eyes. Right now he can't see. He thought he was blind, but his vision did come back after some time. But right now he thinks, okay, if they eject, they might lose their eyes.
His eyes started bleeding, and for approximately 10 minutes following his famous run, he could not see. But later in the hospital, his vision started returning. He also sustained blisters all over his body. Dust particles impinged upon his skin right through the flight suit he was wearing, and raised rather interesting looking welts, which fortunately went away.
So the dust particles, not as big an issue up high, not as much dust up there, but certainly the G's are something to be aware of. But he made a full recovery. And which is the other one? World record.
It fell to the lot of two other Air Force officers, John Paul Stapp and Eli Beading, to demonstrate that men could withstand G-forces as they would be experienced during a rocket launch and re-entry. On the Holloman rocket sled, Stapp reached a top speed of 640 miles per hour and slammed to a full stop in 1.4 seconds. suffered no serious or permanent ill effects from the 55G peak deceleration load he took. Beat.
This one is pretty amazing. So this is negative G's because it's on your back. You're going to see his entire skull is going to, well, watch.
Dean subjected himself to an incredible 83 Gs in a later test made on the shorter Daisy track.
So that's 83 Gs. So it's all about the angle your body handles it at. So this is why, for example, when you watch the Apollo astronauts or modern astronauts, they're all sitting on their back with their legs up, because if they hit the ground, your body can handle that way better than hitting face first.
Beating went into a state of shock and for a time was considered to be in a critical condition. 5 days later, however, he was back at work with no permanent disability. These and other intrepid human volunteers took risks at least as dangerous as those they had required of the animal subjects, and the data thus gained contributed significantly to the successful flights of Alan Shepard, John Glenn, and their successors.
And again, not just for the astronauts, that's where we get most of our data for designing crash test dummies. These were the experiments that did it. Where does G come from? Next class, we're going to do an activity where we're going to try to calculate G. Let me hit pause for 1 second here.